It's a recognized concern that General Electric circuit breakers may exhibit a slower tripping response during ground fault events when compared to other brands such as Square D or Siemens. This difference in performance is primarily attributed to the design and operational principles of the circuit breakers themselves. General Electric circuit breakers typically employ a thermal element as their primary mechanism for detecting and responding to overcurrent conditions, including ground faults. A thermal element relies on the heat generated by the current flowing through it to initiate the tripping action. When an overcurrent or ground fault occurs, the increased current flow causes the thermal element to heat up. As the thermal element heats up, it eventually reaches a temperature threshold that triggers the breaker to trip, interrupting the circuit and stopping the flow of current. In contrast, other brands of circuit breakers such as Square D and Siemens often utilize a magnetic element, either alone or in conjunction with a thermal element, to detect and respond to overcurrent conditions. A magnetic element operates based on the electromagnetic field generated by the current flowing through it. When an overcurrent or ground fault occurs, the increased current flow creates a stronger electromagnetic field. This electromagnetic field exerts a force on a magnetic armature, causing it to move and trigger the breaker to trip. Because the magnetic element responds directly to the current flow and does not rely on heat buildup, it typically provides a faster tripping response than a thermal element. The speed at which a circuit breaker trips during a ground fault is crucial for safety. A faster tripping response minimizes the duration of the fault current, reducing the risk of electrical fires, equipment damage, and electrical shock. In situations where a ground fault occurs, such as when a live wire comes into contact with a grounded metal surface, a significant amount of current can flow through the unintended path. This current can generate heat, which can ignite nearby combustible materials and start a fire. A circuit breaker that trips quickly interrupts the current flow, preventing the heat from building up and reducing the likelihood of a fire. In the specific scenario described, where a switch leg became jammed between a metal screw and the connection screw of a GAN box, the General Electric breaker did not trip quickly enough to prevent the wire from burning through. This is because the thermal element in the breaker did not have enough time to heat up and trip the breaker before the wire was damaged. This situation highlights the importance of selecting circuit breakers with appropriate tripping characteristics for the specific application. In situations where a fast tripping response is critical, such as in circuits that supply sensitive electronic equipment or in areas where there is a high risk of ground faults, it may be advisable to use circuit breakers with magnetic elements or other fast-acting tripping mechanisms. It is also important to ensure that circuit breakers are properly sized and installed in accordance with applicable electrical codes and standards. The National Electrical Code, or NEC, provides guidelines for selecting and installing circuit breakers to protect electrical circuits from overcurrents and ground faults. Article 240.4 covers the protection of conductors against overcurrent. This section specifies the requirements for overcurrent protection devices, such as circuit breakers and fuses, to protect conductors from damage due to excessive current flow. The size of the overcurrent protection device must be matched to the ampacity of the conductor it is protecting. Ampacity is the current carrying capacity of a conductor, which is determined by its size, material, and insulation type. The NEC provides tables that list the ampacity of different types of conductors. For example, Table 310.15b16 lists the allowable ampacities of insulated conductors rated up to 600 volts, not more than 3 conductors in a raceway or cable or earth. If the overcurrent protection device is too large for the conductor it is protecting, the conductor could overheat and be damaged, potentially leading to a fire. Conversely, if the overcurrent protection device is too small, it may trip unnecessarily, causing nuisance outages. Article 250.4 covers the grounding and bonding requirements for electrical systems. Grounding and bonding are essential for electrical safety, as they provide a low impedance path for fault current to flow back to the source, allowing the overcurrent protection device to trip and clear the fault. This article specifies the requirements for grounding electrodes, grounding conductors, and bonding conductors, which are used to connect electrical equipment and systems to the earth. Grounding electrodes are typically metal rods, pipes, or plates that are buried in the earth. Grounding conductors are used to connect electrical equipment to the grounding electrode. Bonding conductors are used to connect metal parts of electrical equipment together to ensure that they are at the same potential. Proper grounding and bonding helps to prevent electrical shock hazards by providing a path for fault current to flow back to the source, allowing the overcurrent protection device to trip and clear the fault. If electrical equipment is not properly grounded and bonded, a person could come into contact with a live metal part and receive an electrical shock. Article 210.8 covers ground fault circuit interrupter, or GFCI, protection for personnel. GFCIs are devices that are designed to protect people from electrical shock by detecting ground faults and interrupting the circuit. A GFCI works by monitoring the current flowing through the hot and neutral conductors of a circuit. If there is a difference in current between the two conductors, it indicates that some of the current is leaking to ground, which could be a sign of a ground fault. If the GFCI detects a ground fault, it will trip the circuit, interrupting the flow of current and preventing electrical shock. GFCIs are required in certain locations where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor areas. The NEC specifies the specific locations where GFCI protection is required. In addition to the NEC, other electrical codes and standards may also apply to the selection and installation of circuit breakers. These codes and standards may vary depending on the location and the type of electrical system. It is important to consult with a qualified electrician to ensure that circuit breakers are properly selected and installed in accordance with all applicable codes and standards. A qualified electrician can assess the specific needs of the electrical system and recommend the appropriate type and size of circuit breakers. They can also ensure that the circuit breakers are properly installed and tested to verify that they are functioning correctly. If there are concerns about the performance of existing General Electric circuit breakers, it is advisable to contact an electrician to have them inspected and tested. An electrician can use specialized equipment to measure the trip-in time of the circuit breakers and compare it to the manufacturer's specifications. If the circuit breakers are found to be tripping slower than expected, they may need to be replaced. Replacing circuit breakers is a relatively straightforward process, but it should only be done by a qualified electrician. An electrician will disconnect the power to the circuit, remove the old circuit breaker, and install the new circuit breaker. They will then test the new circuit breaker to ensure that it is functioning correctly. When selecting replacement circuit breakers, it is important to choose circuit breakers that are compatible with the existing electrical panel. The circuit breakers must have the same voltage and amperage rating as the old circuit breakers. It is also important to choose circuit breakers that are listed by a recognized testing laboratory, such as Underwriters Laboratories or UL. UL-listed circuit breakers have been tested and certified to meet certain safety standards. In addition to replacing circuit breakers, there are other steps that can be taken to improve electrical safety. These steps include ensuring that all electrical outlets and switches are properly grounded, using ground fault circuit interrupters, or GFCIs, in areas where there is a high risk of electrical shock, avoiding overloading electrical circuits, and having the electrical system inspected regularly by a qualified electrician. Overloading electrical circuits can cause the wires to overheat and potentially lead to a fire. It is important to avoid plugging too many appliances into a single outlet or circuit. The total amount of current drawn by all of the appliances on a circuit should not exceed the amperage rating of the circuit breaker. Having the electrical system inspected regularly by a qualified electrician can help to identify potential problems before they become serious. An electrician can inspect the wiring, circuit breakers, and other components of the electrical system to ensure that they are in good condition and functioning properly. It can also identify any potential hazards, such as loose connections or damaged wiring. In conclusion, the slow tripping response of General Electric circuit breakers during ground fault events is a recognized concern. This is due to the thermal trip mechanism used in these breakers. In situations where a fast tripping response is critical, it may be advisable to use circuit breakers with magnetic elements or other fast-acting tripping mechanisms. It is also important to ensure that circuit breakers are properly sized and installed in accordance with applicable electrical codes and standards. If there are concerns about the performance of existing general electric circuit breakers, it is advisable to contact an electrician to have them inspected and tested and replaced if necessary.